Well, good morning, everybody. It's a real pleasure to introduce Guillaume Thomas, who you probably all know already. But anyway, Guillaume has been defended his PhD thesis in Strasbourg. Then he moved to Victoria in Canada with a postdoctoral fellowship. And he has been with us at the IAC since 2020, when he joined first with the Juan de la Cierva Fellowship, and then on several postdoc in support of WEAVE surveys. Guillaume is research interests are very broad. They are more in the field of galactic archaeology and near-field cosmology. And he approaches the questions in this field using a variety of techniques. He's an expert in embodied modeling, dynamical modeling, the use of the best data sets from large surveys, and also machine learning. And today we'll be telling us about reconstructing the accretion history of the Milky Way using all these amazing data sets and techniques.
So thank you very much. So today I'm going to speak about the history of the Milky Way and how the next generations of large spectroscopic surveys, but also photometric surveys, will help us to reconstruct the formation of the Milky Way, but also to understand what, or to do a cartography of the galactic potentials at either in the center of the Milky Way, but also at large distances. So maybe the first question that all of us ask is, how in the standard cosmological model, a galaxy like the Milky Way is formed. And the best way is maybe to go directly to the large-scale simulations. And here you have the video or the movie of the formation of such galaxies. And you see that the galaxies in the center, the Milky Way, is formed through a succession of accretions of smaller galaxies, either by galaxies that are accreted radially, that form in that case is really long structure shells. You can see that in that case, the galaxy doesn't survive really long. Or in most of the cases, some accretion that are tangentials and that form long structure called stellar streams. Plus, on top of that, you have also some accretion of gas along the spiral filaments. And at the end, you have something like the Milky Way. And that's the basis of the hierarchical formations. And the hierarchical formation is not something really specific to lambda CDM, right? You can go to other type of dark matter, or majority of type of dark matter, plus also some alternative gravity theory, and you always have this basis of the formation of the galaxy. So we have plenty of galaxies in our universe, and a lot of question for people just doing galactic formations is, why do we care of the Milky Way? It's just a normal galaxy, it's a standard galaxies. Well, first of all, we are not that sure that the Milky Way is something standard. That's something that we have to prove. Then the other thing is also that the Milky Way is right now still the best galaxies that we have in terms of data. So we can really have complementary data to give informations that are going to complement what we have, for example, with GWST at high redshift. So in terms of structures, the Milky Way is usually presented as a galaxy, as a disk galaxy, where you see clearly here the disk in the Gaia images with the Magellanic Cloud here. And you can typically decompose in the disk, the rest is the halo, the part of the bulge, and so on. That's the typical view of the Milky Way. And so, as I was saying, the Milky Way is something specific because we have at the same time dynamical and chemical information that we cannot have for other galaxies for individual stars. And in particular, in that cases, Gaia has been really helpful to understand the evolution of the Milky Way, because we have access with Gaia to detailed dynamic of the stars with proper motion for more than 1.8 billion stars, line of sight velocities for 33 million stars. These are the best spectroscopic surveys right now. Chemistry for 5.5 million stars. And here we have a very nice picture of it. So this gives us access to the 6 dynamical informations for the galaxy. On top of that, Gaia is also complemented by other spectroscopic surveys, which allow us to go deeper and to use the full depth of the Gaia data. Spectroscopic velocity right now is limited to a given magnitude, around 17. And this allows us to go deeper in particular surveys like Segway, Lamost, Apogee, Gaia, Gala, and in the next generation of surveys that I'm going to mention. Also with the photometry is extremely helpful because it can help us to cover not the parts, the optical wavelengths covered by Gaia, but also to go from the near UV to the near infrared, which allow us, for example, to get photometric chemistry, so to complement also spectroscopic data in the cases. Also, we can also have information from astroseismology, which allow us to have individual ages for individual stars. So you see that really the Milky Way is something really that we have all information that we cannot get for any other galaxy in the universe up to date. And so this, for example, is extremely useful because it allows us to study the Milky Way and to show that, for example, it's not in equilibrium. It's been shown really recently with high-resolution numerical simulations that the LMC is not in equilibrium due to the massive accretion of the Large Magellanic Cloud. As you will see here in this movie, the Large Magellanic Cloud, when it's accreted to the Milky Way, as currently we estimate the mass to 1/10 of the mass of the Milky Way, and you see that it's going to be attracted by the Milky Way, but also it starts to shift the disk of the Milky Way from the barycenter, and this generates modifications of the velocity reference frame, especially in the part of the halo. And on top of that, it also generates dark matter wake. So first you have the collective responses, which basically correspond to this drag here of the disk, so of the shift of the barycenter, and the transient wake, which is the typical Chandrasekhar dynamical friction tail. So usually when you have such a massive accretion, you can imagine that you have like in a boat and you have the water falling around, and the water in that case is dark matter particles. And the dark matter particles are going to stuck a bit behind because it's going to be attracted by the galaxy. And so it's going to form a tail of particle behind it, which with this over density is going to break slowly the progenitors. And usually that's why at the end you have some really radial accretions for massive galaxies. So all of this, for example, is something that we can do just in the Milky Way because we have the data to do so and to study a galaxy not in equilibrium. And it's something which is completely different that we do with other galaxies, where we usually assume that they're in equilibrium or they are relaxed or virialized, which, as we see in the Milky Way, is not the case. So here's the goal of trying to reconstruct the accretion history of the Milky Way is to find the debris of the accreted galaxies. So which is, well, I studied as a simulator. The idea will be to try to reconstruct the merger tree as we have in the simulation, such that we can compare the merger tree of the Milky Way with the merger tree in the simulation, ideally with different type of dark matter, with different gravity, and to compare really the Milky Way with typical galaxy like the Milky Way, and to see first if the Milky Way is something which is standard compared to the other galaxies, but also to try to constrain these different models, either the type of dark matter present in the local universe, but also the bionic physics that we implement in the simulations. So the next question is, okay, we want to detect the debris. Fine. And which form can we detect this debris? So we can typically detect it in two broad. Either it is spatially results in terms of surviving galaxies, as you see here, clearly, relatively easy to detect. You will see why I say relatively easy. Otherwise, Josephina is going to jump on me, I think. Tidal streams, which is this long filament, which is due to the tidal disruption, so we have the dwarf galaxies. You have also some shells, which has these long filament structures. Usually this form when a galaxy is accreted radially. So you're going to disperse all the velocity of the stars there and forming these long structures. However, in the Milky Way, this is something problematic. We see these shells in external galaxies, and in particular in integrated light. We can clearly see the shells. The problem is that we are living inside the Milky Way. So to detect this, you need to get, first of all, precise distances. And also here, it's helped a bit the fact that when you see external galaxy, you have a projection effect, which is that you can add a bit of the column density to get the contrast, which we cannot have in the Milky Way. And so that's one of the problems. But here, really is the biggest problem is to get the distances of stars. And maybe for some of you, it's going to be a bit weird, but it's extremely hard to get precise distances of stars in the Milky Way, and especially in large distances. And for example, we can use a few tracers, which we have really precise distances like RL-Iris, BHB stars, but they're not that present in the galaxies. And so we cannot really detect the structure with that. And with the other type of stars, the precision of the velocity right now, the distances is around 15 to 20% maximum, really. So again, it is not enough to be able to see this. So anyway, so that's the spatial results. The other type of structures is all the stars that you see in the rest of the halo that form a non-spatial resolved object. They're just galaxies that are completely destroyed. However, we can still detect them through the dynamical properties, but also the chemical properties. And I'm going to show that next. So spatially resolved object. Let's speak first of surviving satellite galaxies. So galaxies that we still see orbiting around the Milky Way. So as I was saying, they are relatively easy to observe. For some classical dwarfs, it's relatively easy. That's from the paper that we published with Josepina a couple of years ago. Where you can clearly see, for example, the position of the stars from Ursa Minor, and also the properties in the color magnitude diagram, which is a kind of a DNE of the galaxies, and you can clearly identify the stars here. On the other side, you have also some other galaxies that are extremely hard to detect because they are just populated of a couple of stars. As you see here, that's a dwarf galaxies, not that easy to detect. And right now, the galaxy with the lower mass that we have is populated of 12 stars. So in the entire galaxy, we can detect all the galaxies populated of 12 stars. So not that necessarily easy. So right now we have a census around the Milky Way, around 60 to 70 dwarf galaxies around the Milky Way. This is uncertain because some of the object, we don't know if it is globular clusters or dwarf galaxies due to the dynamical dispersion. We're still not entirely sure, and there's some discussion. And also this number is slightly growing. It's been growing really quickly in the 2010s with the advent of digital surveys. And now it's been going less than before. And the interesting point of that is that for most of the galaxies, we have 6 dynamical informations because they are still compact objects. So we can just use the statistics of the velocity of the galaxies that you have to get the systemic motion. So to know how they moved around. And when you have the 6 dynamical information, what is nice, you can assume the galactic potential and you can reconstruct the orbit of this object. And it's what we have been doing. And we have doing 2 assumptions. First of all, we studied the case of an isolated Milky Way. So just a typical disk with a bulge following an NFW, and you can reconstruct the orbit, the orbit that you see in orange. And in the second cases, where we included the perturbation generated by the accretion of the massive Magellan cloud, which is going, as I was saying, to drag the disk and to move it outside from the barycenter, but also to generate some perturbation in the halo. And that's the one that you have in blue. And what you can see is that under these 2 different assumptions, for some of the galaxies, the orbits are relatively similar. You have a bit of the change, but you still see the same periodicity. In other galaxies, you have some really drastic changes, as you can see here. From the case when it is isolated, you see the galaxy Bootes 1 can go really far away to 110 or 20 kpc. Whereas if you take into account the perturbation of the LMC, you see, first of all, that the period is not that much regular. You have a bit of a shift in the pericenter, but also the apocenter is way different than what you have when you don't include these perturbations. Another way to see that is the difference between the case without the LMC and with the LMC in this pericenter apocenter diagram. So here the color inverted, but not the same group, I think. and that's all. And you can clearly see that for some galaxies, the difference is really minor. But for some of them, the difference is extremely important. And so there is typically 3 types of galaxy. And that reference to the nice movie, you know, the bad, the unbound, and the ugly. So let's say, so the bound one is a galaxy which, regardless of the potential you're going to take, it's bound for the Milky Way for a very long time. That's the case of Phonax, for example. And you see that's a bound galaxy because you can clearly detect a pericenter and apocenter, and it's going to oscillate for this forever and ever if you trace back. You have the unbound. That's a galaxy which clearly is not linked to the Milky Way. Typically, we estimate the size of the Milky Way to be something around 300 kiloparsec. You see that here, the pericenter, even right now, and time t equals 0, is still higher than 300 kiloparsec. So that's a galaxy which is outside the Milky Way. And then you have the backsplash. And this one is something which is a bit weirder. It's a kind of an intermediate. It's a galaxy which is entering towards the Milky Way, but at such velocities that is not going to be catch or to stay bound to the Milky Way. We're just going to pass in and then going up. And that's clearly what you see here in that galaxy. You see it's coming from some higher than the visual radius, passing inside the Milky Way, reaching the pericenter 1.5 giga years ago, and so in going back, and right now it's still at the distances around 300 kiloparsec. Then you have a few other type, the flyby or the nasty one. And this one is, well, it's a nice example of when you take into account the LMC perturbation, you see that the orbit is completely different in that case, right? Even though the galaxy is currently located at more than 400 kiloparsec, even for such a currently distant galaxy, the LMC can have an impact. And what you can see is that in that case, that's a galaxy which is really a flyby. So it's passing inside the visual radius of the galaxy. But contrary, for example, to LEO ones that go to 100 kiloparsec or even 50, something like this, that's something that stays in the outer part of the galaxy. So it's just going to disturb you a bit, but it's going to continue its path. And then, so you have here a list of what we think are unbound galaxy backsplash. You see that for some of them is uncommon, like NGC 6822, because depending on the potential, the story might be different. But that's basically a census of what we have right now. And so with this type of orbit, it's really nice because, well, you can assume the potentials and to try to reconstruct the orbits, but you can also, for example, assume the distribution function of the galaxy. So typically, O's are distributed spatially and in velocity to then infer the mass of the Milky Way. And this has been done, especially these papers that I really like from Korea Magnus and Eugene Vasiliev, where they used the proper motions, the line of sight velocities of dwarf galaxies and globular clusters, taking the case where they ignore the LMC. So when you have a Milky Way which is isolated for several giga years, and then taking into account the perturbation of the LMC. And here, what you see is in the case where, so you have the part of the data, of the true data that's from simulations. When you take into account the distribution function of globular clusters, you see that you have a lot of information in the inner part of the galaxy. That's normal. Globular clusters tend to be closer to the disk or to the center of the Milky Way than dwarf galaxies that are farther away in the distribution. And you see that at large distances, when you pass 20, 30 kpc, most of the information of the highest precision is coming from satellites. And here it is, when you take into account, so separately, you see that you can have some mass variation. And the green one in the bottom is when you join the information of both of them together at the same time, and you see that you can clearly have some really nice mass estimation, really precise, which is relatively close to the truth, to the true distribution that they assume in the simulations. And so with this method, they were able to estimate the mass of the Milky Way. So in blue, that's without the LMC. In that cases, you have a mass of the Milky Way around 8.5 10 to the power 11 solar masses. But you still see that you have some quite a bit of the distribution. And in red, if you take into account the LMC, you see that the mass is lower. It's going to 73 solar masses. And also, in that cases, they were able to estimate the mass of the LMC to be around 1.65 10 to the power 11 solar masses before accretions, right? So it's not the mass right now of the LMC, but the mass before its accretion. And you see that typically it's around 1/10 or a bit more even of the mass of the LMC. So that's what we can consider a massive merger. So as I was saying, we can reconstruct the orbit with dwarf galaxies because we have the dynamical informations, and that's what we have been doing, assuming the mass of the LMC on the Milky Way. And what is nice is that you can see that if you take into account the LMC, you have some dwarf galaxies that seem to orbit around the LMC. So the LMC it's shown by the white plot, and you see that the galaxies are orbiting around the LMC, right? And so what you can conclude is that a long time ago, these galaxies weren't galaxies or satellites of the Milky Way. They were satellites of the Large Magellanic Cloud. So, and it's normal in the lambda CDM model. You have an accreted galaxy come with its cohort of galaxies. So when you have a massive accretion, these massive galaxies are also its own satellites. And these own satellites, most of the time, are going also to fall with the galaxies, and then are going to be part and become part of the cortege of the satellites of the major galaxies. So in that case, it's like the LMC giving its satellites to the Milky Way. And this has a pretty importance regarding what we call the missing satellite problem, or the number of satellites around the Milky Way. Because if this galaxy were a satellite of the Milky Way, let's say 1, 2, 3 giga years ago, well, we are missing some satellite compared to what we expect in the numerical model with lambda CDM, for example. So here is the census of the satellite that we think were bound to the LMC. And you see that there is a big discrepancy for some satellites. For some of them, we don't know. For some of them, it's sure. Regardless of the people, of the studies, they're always sure. Here, that's the job, the work that we have been doing. And here it is, the ones that have been done really recently by the study of Korea Magnus. So in our cases, we think that there is at least 7 satellites, maybe more. For example, GRUS-2. GRUS-2 is one, I think, the orbit has been trapped. So it's an orbit that has been passing close to the LMC, and it's been trapped by the LMC. But I think it was a satellite of the Milky Way before, and just it's been perturbed recently. Another case is Tucana 4. In our analysis, it's not bound to the LMC, but it's also because it's passed really nearby the LMC really recently. And in our study, we did not include the effects of the small magnetic cloud. And in that case, you can easily imagine that if you have a galaxy near the LMC, you will have a free body interaction at some point if you include the SMC that can kick out these galaxies. So I think that's why also Tucana 4 might be also a galaxy or satellite of the LMC. However, so that's the idea that the LMC had been accreted really recently, 3 to 4 gigayears ago. Really recently, Eugene Vassiev proposed that the LMC is a backsplash galaxy that already interact with the Milky Way between 10 to 8 gigayears ago. And in that case, the number of satellites that were around the LMC are not at all the same. In that cases, you have even 4 classical dwarfs that have 50% chance of belonging to the LMC system: Carina, Draco, Phonax, and Ursa Minor. So that means that the LMC had a really high number of massive satellites, especially when you compare to lambda CDM model. That's something which is absolutely not possible to have. It's around the 3 sigma uncertainties that you have in the simulations. And also that means that the LMC is, that on the other side, the Milky Way doesn't have enough dwarf galaxies around it compared to what we think in the standard cosmological model. So this, if it is the case, that's thickening a bit the plot of the missing satellites in the Milky Way, or in the other side also too much satellites in the LMC. And yeah, that would be really interesting to see the advent of it with new observations. So let's move to stellar streams. So let's move now in things that I personally really interested in because I did my thesis on it. So stellar streams is formed by the disruption of dwarf galaxies or globular clusters by the tidal fields generated by the Milky Way. So you can imagine that your galaxy is like the sea. It's a sea of particles. And the Milky Way is the moon. And the moon is going to generate some tides, right, due to its position. That's exactly the same. You're going to modify the morphology of dwarf galaxies. But at some point, the moon is too massive. So the galaxy is too massive that the deformation is too important. And the stars are going to escape from the Lagrange point. And that's going to form the leading arm and the trailing arm. And at the end, you form structures like this that are still coherent for several gigayears. And coherent means that you can still detect it, especially for several gigayears, typically 4 to 5 gigayears. But it depends of where you are located in the galaxy. If you are farther away, you have less perturbation. The dynamical time is larger, so you can detect the stream for longer. If you are closer, you have a lot of perturbation. The Milky Way is a mess, so you're going to detect it for less than a gigayear. So that's the census of globular cluster of stellar streams that we have around the Milky Way. We know right now more than 90 streams. Most of them have been detected by Gaia. Before Gaia, we knew 10 maybe, something like this. For sure, we knew 4 of them. The other were candidates. Gaia helped us to go from 10 to more than, I think right now we still have even to 100 streams right now. And stellar streams are really interesting because contrary to globular clusters, or to dwarf galaxies, sorry, they are not just giving you an images at a given time. They are like a movie, if you want. You have a different snapshot with different time, because in that case, the particles that are here can help you, for example, to reconstruct the orbit of the galaxy. So you can also get rid of the assumption of the potential that you have behind to reconstruct it, at least in first assumption. And so stellar streams are really useful, for example, to study the perturbation generated by the LMC. that have been done in particular by Denis Circle, we show that in that cases, to reproduce the often Chenab streams that you have here the observation, and here it's simulations, you need to have a perturbation generated by the LMC to explain this kick that you have in the observations. And basically what it is that the streams orbit really close to the LMC. And this perturbation of the LMC, so the LMC shown by the black point here. And you see that at some point the LMC go very close to the streams and is going to alterate up here the velocity vector. Normally a star along the streams is going to follow the streams, right? If you want the stream to be consistent, you need the stars to move along the stream and so to follow the next stars. So normally the arrow should follow the streams as you see here. However, with these perturbations, you add a kick of velocity to the stars, and so the stars are not going to follow the rest of the stream and to be aligned, but are going to go completely perpendicular to it. And you see like clearly that here you have a big drop, but the stars here that did not feel the perturbation are still continuing towards the trend here. So, for example, this type of object are really useful to detect the perturbation of the LMC. The other one really obvious is the Sagittarius, because if you want to reproduce at the same time the morphology of Sagittarius, the velocity, you really need to include this type of perturbations. Also, we recently shows that stellar streams are really nice if you want to study the velocity of the galactic bar. Here you have some simulations with different pattern speed of the bar of an open cluster streams, the IACTalks, not the moving group. So not the, because sometimes people use the same terminology for the IACTalks moving group and IACTalks streams. IACTalks moving group is detected in just in velocity. And it's not stars that were part of the open clusters that have been destroyed, disrupted by tidal fields. That's stars that were in the neighborhood of it, but that were not part of the open cluster. What I call here the streams is really the stars that were belonging to the open clusters that have been stripped away due to tidal fields. And what you see is that for different velocities, you will have different morphology. Clearly, sometimes it's super short, sometimes it's super extended, and also it's going to perturb the inclination of the streams compared to the orbit. So the orbit are shown red. And you see that with some velocity, sometimes the stream doesn't align anymore with the orbit. Sometimes it's even almost perpendicular to it. So if you want to do this plot, that's the deviations of this angle compared to the pattern speed of the bar. And you see that typically we have been able to show that if the streams is inside the co-rotation radius of the bar, most of the time you are not perturbed. So the bar is not able to perturb you, sufficiently to modify the global morphology of the streams. However, past these distances, you see that you start to have a strong deviations. In red, this is the velocity that we think is the pattern speed of the bar right now. And you see that you reach a minimum toward that specific location. And then you reach again, you go higher and you reach a plateau when the IACTalks is around the open outer-Lindblad resonances. And that's something really interesting because that shows that with different stellar streams locating around the disk, we will be able to have an information of the pattern speed of the bar, but also to study its evolution, its dynamical, its timing evolution. Because numerical simulation shows that the pattern speed of the bar, depending how you measure it, is not constant in time. It's going to decrease due to dynamical friction between the stars and the dark matter halo. So you're going to lose angular momentum. So the pattern speed is going to decrease. But on top of that, you have also some fluctuation, which, depending on if you compute it, might be due to the recombination between the bar and the spiral arms. You can imagine you have the spiral arm like this, and sometimes the bar is going to reach the spiral arms again, and so you're going to detect a bar which is longer in that cases, and which also slower. And so with the different type of object, we show that it's possible to study the evolutions of the bar, but also of the spiral arms. And this will be extremely useful because we will get a lot of stars of streams inside the disk for which we'll have velocities, and so for which we'll be able to study this. Then another thing also which is pretty interesting, and it's I think it's in the plot of many large-scale observations, spectroscopic observation, is to measure the granularity of the halo. So the granularity of the halo is just to measure the number of dark matter subhalos that you have in the dark matter halo around the Milky Way, because your halo is not smooth, you have a lot of granularity inside, and this is dependent on the type of dark matter, you will have different level of granularity. You see that cold dark matter, you can have a compression at every scale. It's a linear scale factor. You can have even really tiny dark matter subhalo that do not contain stars inside because the stars or the gas have been evaporating due to feedbacks processes. Whereas in warm dark matter, in that cases, you are not able to form, for example, dark matter subhalo below 10 to the 5, 10 to the 6. That's depend a bit. And different type of dark matters then will have an impact on the level of granularity of the halo. And this has been shown that stellar streams are perfect probe for this because that's dark matter subhalo, for which you don't have any visible tracer to detect it. So you need to detect it in an indirect manner. And that's what's shown, again, Denis circle, where for the Palomar 5 streams, where you have the case of an n-perturbed streams, and here the streams perturbed by 2 dark matter subhalo. And you see that the dark matter subhalo are passing nearby the streams, and is going to generate some strong perturbations along it, and it's going to give a kick, an impulsion of the velocity of the stars. And the stars are going to first be attracted by the dark matter subhalo passing nearby. So they're going to contract, because they're going to get locally a little over density. And the stars are going to continue the path at the end, generating a gap that you see here. And the gap here, or the size and the intensity of the gap, is degenerated between the mass of the dark matter subhalo, its velocity, and its angle of impact, so its orientations. However, the problem, and that's things that I've been spending a lot of time to show, unfortunately, the Milky Way is a mess, and a lot of things can generate these gaps. Not only dark matter subhalo, which the scientific method should tell you that will be the last hypothesis. You should try all the other hypotheses to explain that these gaps are not, well, cannot be explained by any other things else. And the problem is that if you follow some of the paper, we already detected dark matter for 20 years, at least 100 times with this type of methods. And so other effects can generate this gap. First of all, photometric uncertainties. Observations are not perfect. With the observations, we show that, for example, we are able to generate that gap, either in photometric survey, but also in Gaia. Gaia is not something which is homogeneous. You have the scanning law of Gaia, which can also generate the same size of the gap with regularity. And some of the gaps that have been detected, that have been claimed to be due to dark matter, we have been able to show that it's just due to observational uncertainties that are not well taken into account. Other effects can also generate this. The bar can generate some gaps. Spiral arms can generate some gaps. Giant molecular cloud can generate some gaps. Perturbation by other galaxies or globular clusters can generate gaps. For example, along another stream called GD1, there is some big feature, a big gap of several degrees, and people thought for a long time it was due to dark matter. And recent paper showed it might be due to the passage of the Sagittarius dwarf galaxies that even if not pass through the streams, can generate long interaction, perturbation that can generate some gaps. Another thing of which stellar stream can be nice also is to study alternative modified gravity theory, and in particular, for example, MOND. So here we have the simulation of a streams called the Palomar 5 streams in MOND and in Newton, using the same code with the same biases inside. Spend a lot of time to test it. And what you see is that in MOND, the leading arm, so this part here, is shorter than the trailing arm, which is not the case in Newton if you don't take into account external perturbations. And the reason is because in MOND, you break the strong equivalence principle. Strong equivalence principle is, shortly said, that the fact that if you throw an apple in the air, it's going to fall at the same speed, regardless if the Earth is in its current location, in the center of the galaxy, or in the middle of the universe, away of everything. In MOND, you break this, because depending of where you are located, depending of the external field, you're going to not have the same boost. MOND basically is a boost of the gravity, and you boost the total amount of Newtonian acceleration, which means that if you're in the middle of your universe, you're isolated, your only acceleration is coming from your own galaxy. If you are near, let's say, globular clusters around the galaxies, you have your own acceleration coming from the galaxy, but also the external acceleration coming from the host galaxy, the Milky Way. And so the boost is going to be less important than if you are isolated. And this effect is able to generate second order effect, an asymmetry of the length of the streams, And what is interesting is that in the observations, you detect that the stream is indeed is asymmetric with the same asymmetry length, more or less, than what we predict in MOND. The fit is not perfect. This was a prediction that we did in the observations. And actually, it's really interesting because this was already started to be observed by Edouard Bernard, who was here for a very long time, in the Pan-STARRS data. And the problem is that you can imagine that we will have detected it for a very long time. The problem is that the SDSS footprint cut where you have also the asymmetry. So we were not able to detect it for a very long time, even if it was possible with SDSS, just because, well, there is no data. So it's pretty interesting. And this is, it's something really complex because right now, there is no good explanation to explain why in Newton, there is such an asymmetry. Some idea have been proposed due to the bar, thing like this, but the bar needed to generate this asymmetry is unrealistic. Too fast, too high, too massive, too big. Anyway, so then let's move to a part which I've been mostly studied now for Gaia, which is a non-spatially resolved object. So non-spatially resolved objects correspond to accretions, to older accretion. So to the accretion that happened, in the earlier stage of the Milky Way, right? So for us, it's really interesting because it's really where we can study the formation of the Milky Way really at really long time ago. And so a big part of the ideas that we have right now in the fields is coming from this paper of Amina Elmi and Tom Dadzuz, which is the properties, the dynamical properties of an accreted galaxy are preserved for a really long time in the integral of motion space. So integral of motion space are dynamical quantities that are preserved if your Hamiltonian doesn't change. In other sense, if your mass of the galaxy doesn't evolve drastically, or if it is adiabatic, so you have a small addition of the masses, these quantities should be the same. At least for angular momentum, energy, the L dot is not entirely preserved, but well, you see, it can be used. And so here you can clearly see that in the simulation that they did, the shape of galaxies that are represented each by 1/4 here, it's still visible 12 gigayears ago, even if you take into account here the observational uncertainties from Gaia. Also, however, this happened in a really nice lab control system, and the Milky Way is a bit more complex. And to detect this, it's been really helpful to have the revolution of Gaia. Well, I'm French, obviously, so I had to use a picture of the revolutions. And Gaia was really a big revolution to understand our own galaxies. It's really something which may be underestimated, but Gaia was set for a really long time for the observation that not going to drastically change the science, but was the observation needed by a lot of different aspects. But in our cases, in terms of galactic archaeology and galactic dynamic, Gaia was really a game changer. And that's really something that have to be shown here. So with Gaia, it's been that we have been able to measure the motion of a lot of stars around the solar neighborhood. And it's been shown almost by the same time by the group in Cambridge and the group in Groningen, or actually by Gaia Deepak, that you have some, in the velocity motions, you have some weird structures that appear. So you have the disk, but you have these long elongated structures that has been called then the sausages, look a bit like a sausages, which people assume to be part from one accreted galaxies. And it is the same if you go in the tumor diagram, which is this Vy, Vx, Vz diagram, that you have the part of the disk, the part of the halo here, and then you have these long elongated structures, which is mostly retrograde, which is below 0 in cases, which have been detected. And these have been already started to be hints with Hipparcos data, with the nice paper of Nielsen and Schuster. And I think that Emma will be able to speak a lot of this paper for a long time. But you can clearly see that it's already been seen here that you have a big retrograde structures. And weirdly, these retrograde structures are also some weird chemical behaviors, especially in the plane of magnesium over iron, with a trend which is lower than the average trend of the thin disk, thick disk on the rest of the halo. So it's already have been in that this massive accretion called now Gaia and sausages have been there for in previous data. And so the idea is that Gaia and sausages is the most massive accretion that had the Milky Way between 10 and 8 gigayears ago, with a mass ratio between 1.4 to 1.8, something like this, that you still have a lot of uncertainty on the massive. And that's the story that we have now with Gaia, complemented by spectroscopic data. We have been able to go farther away to get stars at lower magnitudes. And so we were able to study these structures. And you are clearly able here to detect Gaia stages, but also a lot of different structures. Here you have a map that can be made by Roman Naidu using the ecto shell surveys. The problem is, well, you would like to say that each of these structures is coming from a galaxy, with the assumption that I showed you initially, that what you will naively think. It's not the case. It's been shown already in 2017 that one given galaxy can generate several clumps, as you can see here. It's also been shown by Rob Grant more recently. Again, in pink here, that's one galaxies. And you see clearly that it can generate several clumps. And that's the fact because a massive accretion, you have dynamical friction. The stars are going to escape at pericenter. And so you're going to eject stars at different level of energy. On top of that, you have also all the perturbation of the disk, the bars and so on, that generate this kind of behaviors inside. So one of the problems that we have for a very long time is that the structures also, we can just detect it by eyes. There is no method really developed to detect it automatically until this paper of Sophie Lovedahl and Thomas Ruiz-Salada, was a postdoc, former postdoc here, who were able to develop a method to detect the structures in dynamical space and to link together some of the structures together. The problem, and that's something that we are working on right now, is that, as I was saying, several clumps can be made by one galaxies, but also in the simulation, we see that some galaxies overlap together. Here, each color shows the dominant area by a given progenitor. So in light blue, this is Instituto stars, the disk, let's say, and then each color corresponds to an accreted progenitors. And you see that you have some regions that are blurred by different colors, and that clearly show that some of the local overdensity can be made by not one progenitors, by the accumulation of several progenitors at these locations. So one of the problems that we have right now is we can detect the structures in dynamical spaces. But first, we have to know which clusters can be linked together because they're coming from one galaxies, but also which of these clusters are coming from different galaxies. And I will speed up a bit here. Basically, it has been assumed that we can use the chemistry of the stars. Indeed, we can clearly see that in that diagram where you have manganese, magnesium, aluminum, and iron, which is able to help you to disentangle stars formed really early on and stars formed later due to different ratio of supernovae type 1H, supernovae type Y2. You see that the accreted stars, basically, that are in that blob here, are really different from the rest of the disk. However, you see that this structures is largely dominated by Guillaume sausages. So if you want to search only in the chemical spaces, you're just going to detect Guillaume sausages. So all the accreted stars seems to be in that region. Also, you have a big part of the old disk that might also overlap in that region, and that's something which is working on right now. And so that's why our project that we have here and that we are currently working right now is to combine at the same time the dynamical information on the chemical information to be able to detect accreted galaxies, to disentangle them from in situ potentially, but also to be able to say that structure is coming from that galaxy, this one and this one are coming from this one, and to be able to reconstruct the merger tree. So right now we are able to detect these structures in the solar vicinity, typically around a volume of 3 to 4 kiloparsec. With the next generation of surveys with Foremost and Daisy, we'll be able to extend this from 3 kiloparsec to 35, 40 kiloparsec in the first years. And then later on, we'll be able to extend it until 80 kiloparsec. And with the next generation of surveys, really in 2 decades, if they're accepted, we'll be able to extend this radius from a few kiloparsec to more than 100 kiloparsec here. And this is really nice because in these distances, the dynamical timescales is larger. So these structures are preserved for longer time. We'll be able to detect accretion, older accretion, less massive. And also you're not perturbed by the bar. So you can also remove all of the perturbation that we have right now in the solar vicinity. At the same time, these surveys, complemented by photometric surveys, like unions, LSST, Euclid, I'm not going to mention them more due to time, but feel free to ask me some questions. We'll be able to study the morphology of the Milky Way until this is very reduced, so to really know until which distances really the Milky Way is, and also to be able to do a cartography of the dynamic of the Milky Way until 150 kiloparsec, even with DESI and foremost. So in the next year, we'll be able to do so. So let's speak really quickly at the end of large spectroscopic surveys. That's a nice window, a nice table that I take from Giuseppina, where you have all the different big surveys, spectroscopic surveys coming. And in particular, you see that you have a big differences in terms of resolutions, in terms of wide wavelength coverages, and dedicated facilities. And here, for us, the important part is that since we're in the Milky Way, we need to have a large field of view with a lot of multiplexing stars. We need to observe a lot of stars at the same time. And so in the next years, are coming surveys, or actually already coming surveys like WIV, DESI, and foremost, and maybe in the future, other instrument using 10 meter, 11 meter class telescope there. So let's speak a bit of WIV, since, well, we have a lot of us are really involved here. So I'm not going to speak more about WIV. You know, it's going to be made on the William Herschel telescope in La Palma. It's the MOSS mod is right now under commissioning. And that's a nice picture of the inauguration that was taken on last October, where you can see a lot of people. And we were able to assist to the dance of the telescope. Fortunately, I was not able to find a movie with it, and I did not register the entire part of it. But it was really nice. The no WIV is there. It started to be commissioned, so it's happening. And so we're going also to speak of WIV in the next SEA. So yeah. And so with WIV, we have different teams, and we are going to be able to study at the same time the halo, but also the disk. And you have a lot of importance also in the interface disk halo. And that's something really that WIV is going to help us to do. And also with WIV, we'll be able really to go further away than what we are being able right now. As I was saying, right now we are limiting toward a couple of kiloparsec around the sun. WIV is going to help us to go until really to study the full depth of the halo and to have access to more than 3 or 4 million stars with velocities at the same time in the halo and in the disk. That's really something which is really interesting. And the problem that we have, and I'm just going to quickly finish on it, it's a problem of homogenizing big surveys together. We're inside the Milky Way, and we need to observe at the same time sky from the northern hemisphere and the southern hemisphere, which means that we need to combine spectroscopic data taken by different telescopes, different surveys, different instruments. And the problem is that the calibration might be extremely hard. And that's why we developed a tool called the spectrotranslator. And here's the goal is to translate one base to another. And here you have the problem. All of these parameters, temperature, log G, metallicity, magnesium, you have for two different high resolution surveys, Gala in the south, Apogee mostly in the north, observing the same stars. You see that for the same parameters, the distributions might be completely different. In Apogee, you see clearly the thin disk, thick disk, the halo. In Gala, it's way harder to see. And that's the same stars, same parameters, and more or less the same resolutions. And you see clearly the differences. And the problem is that if you want to combine this survey together to be able to extend your observation, you cannot do it. So that's why we developed this high deep neural network code. And we have been able to, I'm going to pass really quickly there, to translate from a Gala, to translate it on the basis on Apogee. So here we take this data set and we translate it to that basis, and you have the results. And you can clearly see a big improvement in that cases, which means that we can combine both Gala and Apogee, use them on the same scale to remove all the systematical differences between the surveys. And we have been able to make a cartography of the Milky Way, a chemical map. So here you have the map with Apogee, map with Gala transformed. And we have been able to study the average chemical distribution of the galaxy. And we have been able to see that in both the metallicity and in the magnesium, it seems that you have an offset compared to the center of the disk, so in the plane of the disk, you are a bit offset toward northern part of the hemisphere, where this part is more metal rich, but also richer in magnesium, which means that likely the disk is tilted. There is a warp of the disk. And this is consistent with the disk being perturbed due to the passage of the Sagittarius streams, which going first of all to generate this flaring of the disk that go until 8 kiloparsec, something like this, of elevation, the work that we have been doing, but also is also tilting the disk, but also generating or boosting the star formation rate in the local vicinity, as shown Carme, for example. So in conclusions, that's the stories that we have right now of the Milky Way, where you have the mass of the Milky Way and the major trees that people have been trying to reconstruct. Some of these structures are still, let's say, debated, as a kraken, for example, and not entirely sure that it exists. Gaia and Cedius sages, we have good hints that it's an old accretion, 8 to 10 gigayears ago, but other groups find that it's an accretion that occurred 3 gigayears ago. So a lot of things are still really uncertain, even for the most massive accretion, for which we have a lot of data, we still don't know when it's occurred inside. And the new spectroscopic surveys are going to help us to fulfill entirely this merger tree, but also with this, we're going to be able to map the distribution of the galactic potential in the Milky Way, so to know where is located the matter in different radius of the Milky Way, and so also to know how is distributed the dark matter, to measure the granularity of the dark matter halo, and which is going to give a lot of hints about the fundamental nature of the dark matter in the local universe. And I'm going to finish here. Thanks.
Okay. Thank you, Guillaume. Other questions?
Thanks for the talk. So I had a question about whether you know how efficient merger events such as the Gaia Enceladus would be at forming stripped nuclear star clusters. Has this been like simulated, like stripped nuclear star clusters, or like cores of galaxies that could be confounded with globular clusters or something like that?
So yes. So yes, so Gaia and Cedius stages have been discovered mostly by the stars, as I was saying, but it's already tried. A lot of work have been done to link together also globular clusters to these accretions, but also to potentially some other accreted galaxies. There is we have been doing it with the team in Strasbourg and colleague in Germany with Katie Malan, but the problem in that case you still do under the assumption that the energy and angular momentum are preserved, which more recent simulation show it's not the cases. So it might not necessarily be the cases, let's say. So there is still a lot of doubt to know which globular clusters are linked to Gaia and Cedius sages, or which one are coming from other accreted structures or coming from the disk. And so there are a lot of other aspects have been tried to be used. For example, the age metallicity relation. We see for some globular clusters, we have some differences there inside. And this can be helpful also to try to disentangle globular clusters coming from the disk, the globular clusters from Gaia and Cedius sages and so on. More questions?
Okay, in the case of the simulation of the orbits in which you find that with the inclusion of the LMC, some of the dwarfs would actually originate in the LMC, would have been former satellites of the LMC. So they would be already considered Milky Way satellites now, let's say. I mean, they are. But my question is, in that particular simulation, the LMC would be in the first infall, or would already have been orbiting once? Because it feels strange that if it is in the first infall, the satellites would be like the satellites of the LMC would have arrived first in the Milky Way than the LMC itself. And that feels a bit weird.
So in the cases that we studied with Giuseppina, we use the assumption that the LMC is on the first infall, which was a kind of common assumption. But more recently, as I was saying, Eugene suppose that you have coming in the second pass. So you already have been accreted, but passing at 100 kiloparsec, something like this, and then it's coming back on you right now. Yeah, exactly, 8 to But still, it's possible that the galaxy arrived before the LMC, or some of the galaxies arrived before. Like, for example, Carina. In our cases, Carina might be a galaxy of the LMC. And in that cases, first of all, the LMC has a big halo. So the core of the LMC is going to be accreted after the part of the halo, at least. So you have this, it's normal also to expect that this galaxy will arrive before. Then you have also the fact that the LMC is inside a two-body system with the SMC inside, and this can easily eject galaxies inside. However, this requires a really specific and proper modeling of the orbit of it, and it's extremely difficult to do so. So it's completely possible that you can imagine that you have a big galaxy like Carina that have been expelled from the LMC, and it's have been doing its life after that. But still with the orbit, you can reconstruct and say, well, it's been passing by close to the LMC even before its accretion 6 gigayears ago. And that's something which is a bit perplex. And in that cases, for us, the fact which is the most problematic is the uncertainties in the systemic proper motion. So the Gaia DR4 will help us, for example, to get better orbits and to decrease already this factor. But then you have all the assumptions that you do also on the potential, on the mass of the LMC, of its orbital history inside. So you have a lot of uncertainties inside. But still, by trying to tackle different aspects together, you can really get rid of this degeneracy, especially thanks to stellar streams.
You made very clear the importance of LMC to account for the orbits, for understanding the orbits of the dwarfs. What about the other bodies like SMC or Sagittarius? Don't you need to consider those, even though the corrections may be smaller?
No, Sagittarius, for example, is extremely important. It depends really of the scale that you want to study. For me, I'm mostly focused in that case on the halo. And in the halo, the biggest perturber is the LMC. The Sagittarius can generate some effect, for example, in stellar streams, as I was saying, some gaps along GD1 can be due to Sagittarius. Still, we are not entirely sure because it depends on the orbital history of Sagittarius, and the orbital history of Sagittarius depends on the LMC on the Milky Way. So you see that every time that you try to go further away, you add a pile on the uncertainties or the assumption that you have to do. So it starts to be really complicated. However, we know that Sagittarius have a big impact on the disk, because it's near the disk, so we can reconstruct the orbit, and the orbit in a short time scale in the recent past are easy to reconstruct. It's regardless of the potential, you're always going towards the same point. And we know it's been passing through the disk, and it's have a big impact, either to boost the star formation history, to generate the flaring of the disk. So the fact that the thin disk is going to expand like this, that's part of Sagittarius, but also the fact that it's slightly a bit tilted like this is likely also due to Sagittarius. So Sagittarius, for example, have a big impact. Then all the other things, we are still working on it. I think personally that the Gaia Sagittarius, for example, have a big impact as well, because it's not homogeneously located inside the galaxy. It seems to be a bit closer to the disk, and it's mostly radial with some weird angles in the best simulations. So it might have also a big impact inside, but it's something that we still need to work on it at the same point to give better constraint in the observational side, but also in the modeling side, that we really need to spend more effort in studying the non-equilibrium dynamical galaxies. And that's just in the Milky Way that we have been starting to do so. A bit in M31, but in M31, we will not have proper motion as precise as in the Milky Way, even until 2050, 2060, maybe if Gaia or Gaia Infrared or Gaia and the Theia or other projects are accepted. So still, we still have to work with the Milky Way to do this kind of studies.
Okay, so thank you again for answering the questions. Please remember that we will have the coffee in the cafeteria, and thank you all for coming. See you next time.